The bar AB is moving along the floor and also sliding on the wall. We are given the instantaneous velocity and acceleration of point V, meaning that we know how the bottom of the bar is moving. And we want to determine the velocity, the angular acceleration of the bar, so how it changes its orientation with respect to the floor or the horizontal line. And we want to also identify the acceleration of the end A. So what's the acceleration of this point? For this problem, we can use the concept of the instantaneous center of zero velocity, where if we have a body that it's moving in any type of motion, doesn't necessarily need to be in pure rotation. It can be rotating and translating. If we can identify the velocity of 2 points in the body, we can determine a point where we can consider the entire body, all the set of points that conform the body, as if they were rotating around that point. So let's assume that we have some body here that has a point with velocity VA and another point here with velocity VB, and then we can think of formulating a point somewhere in space that could describe both velocities by thinking as if the body was rotating around that point. So if I pick this point and then I say that the entire body is rotating around this point, then the velocity of point B will have a tangential velocity perpendicular to the dotted line. So it would go in this direction. However, we see that the direction of the red vector that we just drew is not the same direction of the real velocity of point B. That means that this point is not a point valid to consider all the points as if they were performing rotation. To find the true point that could describe both velocities, we can consider the 90 degrees or the perpendicular direction that we just saw here relative to the direction of the vectors B and VA. So we draw a perpendicular line that crosses point V, and also a perpendicular line that crosses point A. The intersection between both points is our instantaneous center of zero velocity. See, zero velocity. Why is it zero velocity? Because here is the point that we can consider as if the entire body, all the points, would be rotating at this instant in time. So we can think of an angular velocity, omega, that would produce VB and BA if all the points were to be rotating around this point O. you can observe that it satisfies the restriction that BB needs to be perpendicular to the line and BA needs to be perpendicular to the line so that it is a tangential velocity. And the point O is the distance to point O is 0, so here there is only rotation at this instant in time, so that this point has 0 velocity, and thus the name instantaneous center of 0 velocity. Let's use the same concept to solve the problem here. We have the bar with point A and point B. This segment measures 0.4 meters. And then we have a vertical line here and an incline in here. This angle is 105 degrees and this angle is 30 degrees. That's all the geometrical information that we have for the problem. And then let's draw the VB vector, so the velocity of point B that slides along the inclined plane. This is vector VB. And we know that VB has a magnitude of 0.5 meters per second. And we also know that its derivative points in the same direction, and it has a magnitude of minus 0.3 meters per second square. First, let's consider point A now. And since the point is sliding on the wall and this is moving down, then this arrow should be pointing down. But before we do that assumption, let's just think that since the point slides on the wall, the vector VA could be pointing up or could be pointing down. And let's see if our reasoning can determine the direction that it must go without using our intuition. Let's find the instantaneous center of 0 velocity by projecting a perpendicular line that crosses point B, perpendicular to the velocity BB. And no matter if it goes up or if it goes down, the perpendicular is the same here. So we know that our instantaneous center of 0 velocity should locate at this point. If our vector BB points in this direction, then our angular velocity at this instant in time must go on this direction, so that the velocity, the tangential velocity, points in the direction that we just drew. If this is the angular velocity and this is the radius, then our velocity VA must be this one, and this solution is not valid. So here we can prove by looking at the drawing, we can demonstrate that the velocity in VA must go down, as our intuition was telling us. Let's remove this clutter here and continue the solution of the problem. Now we have a relation between the velocity VB and the angular velocity omega given by this distance r1. Knowing that VB, its magnitude 0.05, must be equal to omega times distance r1. We already know the direction of the vectors, so we don't really want to use the direction anymore, and we can just work with the scalar values instead of the vectors, since we don't care about the direction anymore. Now we can apply the same relationship between omega and the distance r2 and the vector VA. So we have that VA is equal to omega, same variable, times r2. From the geometry, we can identify the values of r1 and r2, and thus we know this value and this value. Then with this equation we can determine the value of the angular velocity, and then we can plug in that value here to determine the velocity of VA. We identified the linear velocity, the velocity VA, and the angular velocity omega from these equations, but our problem is asking about the angular acceleration and the acceleration of A. Let's look into our relative vectors description. If we have 2 points, point A and point B, and we have a fixed reference frame n, we can describe the position of point A with a vector. We can also describe the position of point B with another vector, and we can draw a vector between point A and point B. This we call the relative vector that goes from point A to point B. You can see that this creates an equation, RA vector plus RAB vector plus it's equal to RB vector. That means that we can describe the position of point B if we know the position of point A and we know the relative position of point B with respect to A. If we were to compute the derivative of this equation, we would have the same relationship but with velocities. So we have VA plus VAB equals VB. But from the previous lecture, we found that the relative velocity of point B with respect to point A, since this is a rigid body, it must be omega cross R. Then our equation transforms to VA plus omega cross R AB vector equals VB. And now if we compute the derivative of this equation, we will have acceleration of A plus the derivative of this cross product equals the acceleration of B. And we already know how to compute the derivative of a cross product, so let's expand this derivative and we get A vector plus alpha cross RAB plus omega cross the velocity of RAB, which is again omega cross RAB, is equal to the acceleration of B. This expression is important for us to solve the problem, and we will use this expression to solve our suggested problem. But first, let's take a look at this expression. This is again a vector, a loop of vectors. If we see that this description that we defined here is the same as RA plus RAB minus RB equals 0. That means that we went from point O, the origin, to point A, then we went from point A to point B, and then from point B we went back with negative RB, we went back down to O. So this is a loop because it went to B and then came back to the origin, to the original point. So I will save this equation and clear the canvas. Let's save this equation and clear the canvas up right here. That's perfect. So if we look at this expression, it relates the acceleration of A, which is what we want to find, with respect to the acceleration in B, which we know already. That's minus 0.3 meters per second in this direction. And our angular velocity, which we already know, our distance RAB, which is the length of the bar in the direction that is given by the example, 30 degrees down, and well, really 60 degrees down from the horizontal. And all of these terms we know. So our unknowns for this problem are highlighted in green. This is one unknown and this is another unknown. Both are vector quantities, but if you see, alpha is a vector quantity only in the z-axis, so it's alpha scalar in the z-axis. And then the acceleration of point A, since it moves along the wall, it can only go on the y-axis. So alpha acceleration in A is equal to acceleration in A scalar in the direction of y. So truly we only have two unknowns, and we have two equations because this is a vector equation with component in x and component in y. And we can use this expression then to solve for our two unknowns, alpha and AA. And that's how you solve this problem with the convenient instantaneous center of zero velocity.